if you've got an implication, P implies Q, its converse implication is to switch the P and the Q around. Q implies P. I'm not saying anything about whether these implications, which you could write as if-then statements, are true or not. They may or may not be true statements. However, what you can say is if this implication does happen to be true, it does happen to be an if-then theorem that can be proved, the converse is not necessarily true. Sometimes it's true and sometimes it's not true. As a simple example, well, a really simple example of a statement that is true but it has a false converse. If x equals 5, then x squared equals 25 is a true statement, right? That's true. Yes, 5 squared equals 25. I'm not saying anything profound here. Its converse, if x squared equals 25, then x equals 5 is false. Yes, x equals 5 is one example of a number whose square is 25, but of course also x equals -5 satisfies that property. So this if-then statement is a false statement. So here's an example, a simple example of a statement that's true, but its converse is false. As a more complicated example, I like to bring up this one. First, some background assumptions. Suppose F, we're going to do a little calculus here, is a, well, let's say the full hypothesis here. A continuous function on a closed interval from A to B and differentiable function on the open interval from A to B. So that's my background assumption. Here's a true statement. If f prime of x is always positive for all x in the open interval from A to B, then f is a strictly increasing function. Actually, on the closed interval from A to B. That's a true statement. That's true. Calculus books usually label that the increasing function theorem. If the derivative is always positive, function's got to be going up. Its converse is false, though. I forgot the word increasing in there. Its converse is false, even though its converse seems like it should be true. If f is strictly increasing function on the closed interval from A to B, then f prime of x is always positive for all x in AB, the open interval. That's a false statement, even though it seems like it should be true. If the function is going up, how can the derivative fail to always be positive when the derivative exists? One example, one counterexample is good enough to illustrate that this is false. Simplest example I can think of is f of x equals x cubed on, say, the interval from -1 to 1. That function is strictly increasing on that interval. Its graph is going up. Its graph looks like this, but, so it's strictly increasing on the closed interval from -1 to 1, but f prime of 0, for example, is 3 times 0 squared is 0, which is not positive, right? 0 is not greater than 0. And you say, wait a minute. Okay, it's almost positive. It's not negative. Still not good enough. Okay. What's going on here? Mini calculus lesson here. This graph is never horizontal. So why does the derivative equal 0 at 0? It's because it looks more and more horizontal as you zoom in near the origin without actually being horizontal. Kind of weird, wild. What's your question?
So even if the derivative at that point.
Being a strictly increasing function is a property over an interval. It's never a property at a point. So we talk about increasing functions over intervals. Okay. So it's subtle and you might say silly in some ways, but still technically something worth talking about to emphasize.